what would I need to do?
Find the area of the big circle.
And then?
Find the area of the little circle.
And then? Subtract them, right? So, like, for this particular circle, what's the radius all the way to the outside of the bigger circle that you're looking at? The biggest circle, this is a 2 right here. This is a 4 and a 4. That would be if I was going all the way out to the biggest circle. I don't know why I put the biggest circle there other than, I think it was just a target. Yeah. So the biggest circle that we need for this problem, let me say that. That would just be 6, right? That would be a radius of 6. And then the inside circle has a radius of 2. So to find the area of that shaded region, we would do pi times 6 squared, area of the bigger circle, minus pi times 2 squared, area of the smaller circle, right? And that would give me 36 pi minus 4 pi. And the easiest way to leave this answer is just as 22 pi. But you could type it in a decimal if you want. 32, sorry. 32. Thank you. All right. So, let me ask you a question. Could I do it this way? Okay. That's not going to give you the same answer, right? I can't subtract the radii there. I can't do pi times 4 squared. That's going to give me 16 pi, which is not the correct answer there. Because if I subtract my 2 radii there and then plug it into the area of a circle equation, I'm going to get the area of a circle with a radius of 4, which is not what I'm looking at here, right? That's not the same. So notice here, the 2 circles have to be separate, okay? Kids do this wrong a lot. So the circles have to be separate. You have to have the biggest circle minus the smallest circle for these. So the washer method is going to be very similar to what we've already done, but you're going to have an inside radius and an outside radius, okay? So if you're in terms of x, then you're integrating from limits a to b. These will be on the x-axis, and you're doing capital R of x squared minus lowercase r of x squared, okay? And then the pi is out front. It is also possible to like make those like pi capital R squared minus radius capital R squared, because it would be okay here. Like I could do pi times 6 squared minus 2 squared. That would give me the same answer, right? I could factor the pi out, but I can't put those two right there together. All right, so let's look at a problem. We were supposed to find the volume of the solid formed by revolving the region bounded by the graphs of y equals square root of x and y equals x squared about the x-axis. So, first of all, I need to find the intersection points of the square root of x and x squared. What do I do to find that? What? Make them equal to each other? Okay. Because it sounded like you said, make me a wizard or something like that. Which, yeah. Okay. Square root of x equals x squared. And then you will square both sides because you can't do anything with that square root. So you'll get x equals x to the 4th. What would you do now? Subtract the x, so 0 equals x to the 4th minus x. Then factor out of x. And then we can set each one equal to 0. So x equals 0. X cubed equals 1. I will cube root both sides, when I cube root, do I put a plus or minus with it? You do not, because you can take the cube root of a negative number. So you don't put plus or minuses here. It's just going to be 1. So these things are going to intersect between 0 and 1. Now, deciding which function is like your top function and bottom function, I think you need a graph for this. Because otherwise you're plugging in like numbers between 0 and 1 into these equations, and it can be done. It'll work like you use 1/4, but you need to use fractions. The graph, I think, is just easier to do. So, plus I think it's helpful to picture what the graph will look like. So, we're going from 0 to 1. And if we plug in 1 to either one of these equations, we will get 1. So they're both going to go through 0, 0, and they're both going to go through the point 1, 1. The thing you really just need to know here is what those graphs look like, right? The square root of x looks like this. I'm sorry, not square root of x. X squared looks like this. So it is concave up here. But the square root of x is not. Square root of x looks like this, and it is concave down. Yeah, you're going to have a big hole in the middle of this. So, whenever we're doing this, essentially what you're doing is you're finding the volume of the outside figure and the volume of the inside figure, and you're subtracting the two. You're doing those two things pretty much separately, right? So, let's pretend that the outside, which we're rotating around the x-axis. So, which equation is the outside equation? Which one's going to be formed like the outside of our figure when we rotate? The green, right? So, that means what I'm going to do is I'm going to let this green right here, that is my capital R of x. I'm going to write over here, capital R of x is going to be the green graph, which is the square root of x. So if I want to find the volume, if I just had the outside, I would do pi times the square root of x squared, right? Pi capital R squared, and I would integrate from 0 to 1. And on this one, it doesn't really matter which axis you're looking at because they're both the same, but which axis are we looking at? X, because we're in terms of x. Right here, we should have it be x right there. Mm-hmm. If we do top minus bottom, it would be like over here doing 6 minus 2. It would be taking it and like your radius would be shortened and rotated like it's a solid figure, which is not going to be the same as doing the two figures separately. So that is one of the biggest troubles that students have, because if we're doing cross sections like we were doing earlier, it's going to be top minus bottom on that. But the capital R of x is going to go from the very top all the way down to whatever you're rotating around, which I guess, probably, because tomorrow it's going to matter. Today, it's always going to be 0, because we're going to only rotate around either the x-axis or the y-axis today. But we are still kind of doing top minus bottom, but we want it to go all the way to the axis that you're rotating around. So you are doing square root of x. Technically, there's a minus 0 right there. But go all the way to the axis that you're rotating around. Okay. Now, that is just the volume of the outside, like if there was no hole in the middle, right? We need to subtract the part where we have the hole in the middle. So our lowercase r would be, lowercase r of x would be the inside function. Again, we really should, I guess, do x squared minus the bottom, which is the axis you're rotating around, which is 0. today it's always going to be 0. Yesterday it was always 0 because we're rotating around the x or the y axis. Tomorrow we're going to rotate around maybe like the line x equals 2, and that's going to change things a little bit. So our r of x here is x squared. So we would be doing pi times the radius, which is x squared, and we would integrate that from 0 to 1. And then we would subtract these two. So let's look at this, what it'll look like together, and sort of we can kind of simplify it a little bit. You may want to do it completely separately because you might get mixed up if you start trying to put it together. But we're doing the integral from 0 to 1 of pi. Square root of x squared, what is that? Just x. Minus, let's just put the x right there, minus the integral from 0 to 1 of pi. And then what is x squared squared here? X to the 4th. Now, if I want to put those together before I integrate to make it a little easier so I don't have to do this twice, both of these have pi's, so that could be pulled out front, and they have the same limits. So we can do pi integral from 0 to 1 of x minus x to the 4th dx. Now, if you want to start from here, that's okay. This was your capital R of x squared, and this part right here was your lowercase r of x squared. So I set them up separately and then put them together so you can kind of see how it relates to what we've already been doing. You can set up from here. What I find a lot of times is if students do this from here, they don't square it properly and they forget the pi a lot of times. So it might even be, you might even be more consistent if you just set them up separately for that, because you're thinking pi r squared for the first outside, pi r squared for the inside, and then you can put them together. This one is one they'd probably ask you to do by hand. It's not very difficult to do by hand. So whenever you integrate, you're going to get x squared 1/2. And then here you'll get x to the 5th, 1/5. And you are integrating from 0 to 1. So that is going to be 1/2, 1 squared minus 1/5, 1 to the 5th, minus 1/2, 0 squared minus 1/5 times 0 to the 5th. Right here. You don't necessarily have to plug in that 0. I just don't want you to get in the habit of always thinking it's 0, because like cosine of 0 is not 0. Depends on what function you're dealing with. So we're just going to get pi, and then we'll have 1/2 minus 1/5 right here, which is going to be, if we get common denominators, that is going to be 5/10 minus 2/10. So we will get 3/10 times pi, or you might see it as 3 pi over 10 for that. And that would be our volume. So in this particular, like whenever we're doing the water, really, if this was a cup, it would only be really the volume of the inside part here, because that's where the water would go, right? If we were doing this for this. So really the problems that we're doing are going to be fairly simple whenever we get there, because it's just going to be, you're just going to take whatever is your inside, and you're going to find that volume, and that's where the water would go for that. Now, let's say that this was some sort of, like, let's say it had some sort of opening right here, and the shaded area is actually where the water goes, like you're filling up I don't know what in the world you would need this for, that you'd fill it up with water. But if we were filling this up with water and rotating it around, then it would be, that would be the volume. Now, that would be in whatever units you're measuring with. So if like you're measuring in centimeters, it'd be in cubic centimeters. So to change that like to ounces, you'd have to convert it. But it would give you, that would be the volume. This one, it's going to be like almost a cone sort of shape, but kind of curved. But then on the inside, it's going to have like a pointy, like, yeah, hole. I don't think that I have anything that will exactly show us that. It's kind of, the hardest part about doing the cup project is learning how to put all the information into the CAD software that makes the model so we can print it. I could put it into the CAD software and we can make the model, like we could make a 3D model that we could see, but I'm also a little worried about my ability to remember how to do all that. I'm going to have to refresh my memory. It was not easy at all to figure out exactly what to do, and I still was not perfect. The kids helped me a lot on figuring out how to fix stuff that wasn't going right. We just kind of played with it for a while.
There's a 3D graphing calculator. I don't know if it's graph exactly that, but
I'll look into it. We'll see if it'll do it after we get done through with these notes. All right, so 2 says find the volume of the region bounded by the graphs of f of x equals the square root of x plus 1 and g of x equals x squared plus 1 when rotated around the either x-axis or this part right here is going to ask us for the y-axis, and well, I probably didn't leave you enough room, but maybe we can figure it out. We might do this with the calculator anyway when we get to the end. So first, whether we're doing this x-axis or y-axis, we need a kind of a sketch of the graph to kind of figure out what's going on here. We need to know where they intersect. What do we do to find where they intersect? Equal to each other. So square root of x plus 1 equals x squared plus 1. That, we would just subtract the 1s. That gives us square root of x equals x squared. We just solved that, right, on the last problem. So that was x equals 0 and x equals 1 for that. So more or less what's happened is we're just taking the shape we just had and we are we're just shifting those both up 1. So when we think about what the graph of this is going to look like here, we need to go up to 2 on our x-axis. 1 is still sufficient over here. And we've got, let's do green here, square root of x plus 1. It'll go through 0, 1, and 1, 2. And it will look like this. It's just basically that graph we just had. It's been moved up 1. And then our red graph here is a quadratic that's been moved up 1. And what could we say about the area of this figure right here compared to example 1? The area should be exactly the same. Is our volume going to be the same when we rotate it? It is not, because what's going to happen now, it is much further away from our axis. So whereas this last one was not going to have a hole all the way through, right? It was going to be connected right there at the very end of it. So it was going to be like a cup sort of shape with a weird shaped hole on the inside. This one is going to have a hole all the way through it, right? Because right here you've got all of this space right here where you got nothing. So you're going to have, like, it's going to be much bigger and have a hole all the way through this. So whenever we are doing this problem, we will start off with our outside radius. That goes, or when we're rotating around x. That's the function furthest away from the axis you're rotating around, which is going to be your capital R of x. So for this one, capital R of x is going to be the green function, which is the square root of x plus 1. And then your inside is the one closest to the axis that you're rotating around. There's your lowercase r of x, which is our red graph here. R of x is going to be x squared plus 1. So I'm going to put a little bit of this together. Our limits here, what would they be? 0 to 1. Okay, we're looking at the x-axis. Those are our intersection points, right? And I would have pi times the outside radius, square root of x plus 1, squared. Right? Pi r squared, that's our formula there. Then I would subtract, I need to put the inside radius into our area of a formula circle, equation. So pi times x squared plus 1 squared. And I'd put a dx over here on the end. Now, a lot of times when you'll see this, especially if it's just a setup problem, they'll pull the pi out front and they'll write this as pi 0 to 1, and they'll have square root of x plus 1 squared minus x squared plus 1 squared dx like this. We are going to use our calculators here because that one's going to take us a lot longer to integrate by hand, a lot longer. And in most cases, I think they are going to either only ask for the setup or they're going to give you the calculator to solve. So let's use our calculators here. It's part of the area of a circle formula. It's pi r squared. So that's why you've got to square each one of those. And you must square them separately. You don't, because it's pi r squared minus pi r squared. We can't just have like x squared of x plus 1 minus x squared plus 1 squared. You can't square the whole thing. It's squared separately for these, which is different than like our cross-section problems. So for this, I'm going to put a pi integral, and then I need to do square root of x plus 1 squared minus, oh wait, I messed that up because I did not close my square root parentheses. There we go. And type this in, guys, because it's easy to, even though it might not look that bad, typing it in, it's really easy to mess this up. So when I get square root of x plus 1 squared minus x squared plus 1 squared, I have to put comma x, comma 0, comma 1 at the end. And I'm getting 29 pi over 30. And so that is significantly bigger than the 3/10 pi that you got on the last problem. Everybody try it on the calculator. Make sure you can do it on the calculator because getting all those parentheses and squares in the right place is sometimes not as easy as it may look. Check with your neighbors, see if they're getting it. Another option on this is you could use y1 and y2 for your capital R and your lowercase r. That would make it a little easier to type in. Maybe. comma x, comma 0, comma 1. Yeah. Okay, questions? Okay. You're getting an error. Probably your parentheses. You need it. No, you do need it. You need it, but you don't have one. No, you have one. Yeah, oh, no, which is right. You got an extra one after the square. You may have done it on the last part.
Oh, missing a word.
Oh, you have to have a parentheses at the very end. Like you gotta close that at the very end. I think that hopefully is the word. There you go. Okay. Alright, now we gotta rotate around the y-axis on this one also. So I'm gonna recopy this graph down here so we have a fresh graph to look at. And I'm gonna use the same colors I used up here, what I do. Green for the top one. And so we've got the green graph on the top, the red graph on the bottom. Here is our area, but this time we are rotating around the y-axis here. So that means when I'm thinking about my outside and inside radius, it's not the top and the bottom, it's the furthest right and the furthest left, like the furthest away from the axis you're rotating around and the closest to. So, and I need everything in terms of y for this. So, I've got f of x equals square root of x plus 1 for that green graph. So, that's like y equals square root of x plus 1. I'm going to subtract 1. Y minus 1 equals the square root of x. And I got square both sides. So x equals y minus 1 squared. That is this green graph right here. So instead of using the x's, I've got to use the y's for that. Same thing for the other one. The red graph is y equals x squared plus 1. So I would subtract 1 here also. Y minus 1 would equal x squared. I would need to square root both sides. So I will get x equals, technically you do get a plus or minus there, but this would be the positive part because we're in the first quadrant, so we're just going to put square root of y minus 1. That is the red graph right here. So you're rotating around the y-axis. The furthest away graph is your red graph. So your capital R of x, your outside radius, what is it going to be? Oh, and I'm messing that up. I shouldn't do R of x, should I? R of y. And what should it be? Square root of y minus 1. And then when I do the inside, is going to be from the where you're rotating around to the closest graph. So that right there is my lowercase r of x. That's my inside radius. Oh, still using x's. Gosh. All these right here should be y's. So my lowercase r of y, what's it going to be? Y minus 1 squared. Okay, so it's pi r squared minus pi r squared, right? So I'm going to do, what would my limits on my integral be? 1 to 2. I'm looking at that y-axis, and it's 1 to 2. And so I'm going to do pi times my outside radius, which is square root of y minus 1, squared, minus pi times the inside radius, which is y minus 1, squared, squared. It's easy to miss that second square right there. It will probably be a little bit easier to type in if we pull out the pi and we separate things a little bit. So you'll have pi, integral from 1 to 2. And for this part right here, I've got the square root of y minus 1 squared. What's that going to give me? Just y minus 1. And I've already pulled the pi out here. When I do y minus 1 squared squared, what do I get? Y minus 1 to the 4th. All right, we okay here? Oh, I was looking for my mistake. I heard murmuring and said I'd messed something up. Okay here? All right. At this point, again, we're just going to use our calculators for this. It can be done by hand, but it's going to be extensive, and I don't think they're going to ask you to do that on this. So, pi, or you can leave the pi off and just throw it in there on the end. You should have pi in your answers for these. And we're going to do integral of y minus 1 minus y minus 1 to the 4th, comma, y, comma, 1, comma, 2. Anybody want to guess what we're going to get? No. There should be a way you could make a good guess on this one. I've not worked this out since last year. I bet it's going to be 3 pi over 10. Because I think this is going to be the same shape, even though it's around a different axis. I think it's going to be the same shape as example 1. And I'm right. All right, everybody try to type that into your calculator. Make sure you can do it in your calculator because it is easier said than done. You could do the whole thing with x's, like instead of y's, you could type in all x's. But since you use y's, you got to use the comma line. Everybody doing pretty good here. It usually means you've got something missing in like your comma x, comma, or comma y, comma 1, comma 2 stuff there. Yeah, you. Alright, you left off your pi and you left off your the pi you can always just throw back in because it's just all right. Yes. Yes. Yeah. Although that's a hard one to solve. Probably the better way to do it is to set them equal as x's, and then just plug 0 and 1 in and see what you get for your y coordinates. Would be better because it's going to be a lot harder equation to solve this way. You're going to have, you're going to square both sides, and that's going to make that like the fourth power, and then it's going to be hard to solve that way. Another good way is just thinking about what the graphs look like for that, because it is a quadratic, it's been moved up, and think about what those points are, and then square root that's been moved up, and think about those points. Sometimes that might be easier than like algebraically solving them. Okay, questions there? All right, we've got, I think this is our last one here. So we're going to find the volume of the solid formed by rotating the region bounded by y equals x squared minus 4x and y equals x minus 4 about the x-axis. So if they have not given you a graph for this, you got to think about what this is going to look like. So let's do intersection points first. We're going to have x squared minus 4x equals x minus 4. I would move everything to one side. X squared minus 5x plus 4 would equal 0. I will have x minus 4, x minus 1, and that will give me 4 and 1. And so if we think also about what this looks like, this is going to be a parabola like facing upward. And if you think about like factoring this, it's going to be x times x minus 4. It's going to have x-intercepts at 0 and 4. This is going to actually be like below the x-axis. We haven't seen one that looked like that yet. So all of this is actually going to happen like below the x-axis. We got 1, 2, 3, 4. So like you could just sort of think about making a table. If you plug in 0, you'll get, we'll do this one in blue. 0, 0. If you plug in 1, you should get -1. No, -3. Then you'll get -4, -3 again, and back to 0 here. And I'm doing this kind of quick because we're low on time, but it'll look like this. And then you've got y equals x minus 4, which is to say line, so let's do that one in green. Y-intercept at -4, you'll go up 1 to the right 1. My line's maybe going to be a little crooked there. So we're looking at this area here, which is a little funny because it is below the x-axis here. So if we're thinking about rotating this, I've been saying top minus bottom, which has been true a lot of times because we have been rotating, we've been in the first quadrant, right? Or at least above the x-axis. Whenever we rotate around the x-axis here and we're doing our outside radius and our inside radius, we actually don't want to be thinking like top minus bottom here. We want to be thinking furthest away from the x-axis and closest to the x-axis. So our furthest away from the x-axis, our capital R of x, is going to be this. All right, our capital R of x is going to be the blue graph. Why should I do this back? It's not going to matter. We'll just do the blue graph, which was x squared minus 4x. I'm almost tempted to do 0 minus x squared minus 4x, but I think that just makes this more complicated. The square is going to make it work out either way. Because technically that's going to be a negative value, but we don't really care about negatives when we're talking about area, so it'll be okay. And then we want to think about closest to the axis that we're rotating around, so that would be our lowercase r of x, and that would be the inside graph, which is going to be x minus 4 here. And so to set up our integral, what would our limits on our integral be? 0 to 4. I guess I'll go ahead and pull the pi out front on this one. You're going to have power squared minus power squared. They'll each have pi's. I'm just trying to shortcut this a little bit. We'll have x squared minus 4 squared minus x minus 4 squared. Yes. Oh, I'm sorry. It should be 1 to 4. You're exactly right. I let them trick me with their bad answers. Yeah, should be 1 to 4. You're right. I did. Yes. It shouldn't it? Right there needs x. Okay. Have I made any other mistakes? All right. And then we would type this into the calculator, but we have 2 minutes left, and I'm not sure we have time to do that. But let's just say this only asks you to set up and not solve, because they also do that a lot for these problems as well. You would just type it into the calculator from here, so, and I'll give you your answer. All right, your assignment is going to be these problems here, 5, 6, 13b, 15a, 31, 32, 34. Much like Friday's assignment, use your calculator to integrate, because it will take a very long time to do if you don't. I think you did 13A. Yeah. Go back and do 13B because you probably did it wrong if you already did it. Yeah. If you already did it, you probably did it wrong.